Hi guys, welcome back. Today we're going to be talking about Bose-Einstein and Fermi-Dirac statistics and the comparison and what the difference is between the two. So let me get going with that then. Okay, so I'm going to go over here. And one of the things that is true is that Bose-Einstein is dealing with bosons, and Fermi-Dirac statistics is dealing with fermions. And that really means one important thing here, that with fermions, the Heisenberg uncertainty principle holds. But with bosons, it doesn't. So let's take a little look here at this. We're gonna go through a little bit here. So we have a formula here, and this formula here represents the mean number of particles based on temperature and potential energy. And what it does is it really gives you this formula right here. But this formula is used in both statistics. It's used for the Bose-Einstein and for the Fermi-Dirac, but this thing is not used in both. So it's either going to be +1 or -1, and that's the difference. And that +1 is going to represent when we're dealing with Fermi-Dirac, and the -1 is going to be when we're dealing with Bose-Einstein statistics. So let's talk in terms of that and how all this comes into play here. So let me just go through a little bit here with a few things with the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle does not hold for Bose-Einstein because we are not concerned with fermions but with bosons. Bosons have whole number integral spins, therefore the -1 is for the bosons. Photons, helium, examples, sorry guys, of bosons would be photons, helium-4 atoms, etc. The Heisenberg uncertainty principle does hold for Fermi-Dirac because we're dealing with fermions, electrons, protons, etc. And these particles have half-integer spins. Now, what's really neat about this and how all this comes together when we're talking about it, we're getting away from the Maxwell idea, is that these particles are considered indistinguishable. And being that they're indistinguishable, we're cutting down rapidly on the microstates. And that's a big deal. And, so that's going to kind of be how we're going to look at it here now. So when we look at the bosons, and we look at the energy levels and how these particles are distributed or how they're setting up there, we can start to look at this example right here. And we'll notice here that we have 6 energy states. We have 5 excited states in the ground state here. And we have 4 particles here. So what we tend to realize here is that we're going to have, we have the 6 states and we have the 4 particles. So that means that we're going to be able to set up, let me just go through here, we're going to be able to set up different arrangements for the microstates. So there are different ways that these energy levels that we're seeing here, where we have 3 particles in the ground state and we have 1 particle in the 5th excited state, could set up. Now they could set up in these 6 possible distributions here. As stated, there are 6. So if you look here, they add up. So like for the 2nd state here, we have the 4th excited state and the 1st excited state, which is really equivalent to the 5th excited state. And then we have 2 in the 0 state. So yeah, that works. That does work out there, as you can see and stuff. So then as we go through and stuff, as we begin to add up, we're realizing we're getting this number 6 all the time through these states and stuff like that. Now, so when we look at this here, since these particles are indistinguishable, then the bottom line is that we know we have only 6 microstates, but we actually have 24 particles. And because we're looking at the probability of these particles existing in these states, so it's really going to be 6 energy states times 4 particles, which is 24. But we can actually count across our energy states here. And if you look, like, for example, in the ground state here, we really have, for the first one, we have 3. Then B, we have 2, so that's 5. We got 2 more. That's going to be 7, 1 more 8, and then 1 more 9. So you can kind of see that there, that in the ground state here, we're going to have 9. Okay, particles. And then in the first excited state here, we've got 1, and then we got 2 more, we got 3, then we got 3 more, we got 6, and we got 7. So you can see we've got 7 here. And then in the second excited state here, we've got 1, another 1, and 2, which is 4. And then finally, as we get higher up, we get less. But like in the third excited state, we've got 2. And then in the fourth, we've got 1. And then in the fifth, we've got 1 there. So we've got, if we add these up, we've got n equal 24 particles, just as we stated. Now, the difference with, this is the bosons. But the nice thing about the bosons is that they can exist in the same state. The fermions can't, so you're going to get less microstates with the fermions, and that's kind of the deal, even though they're indistinguishable particles. So you are getting a difference. You are getting a difference in the way the statistics is setting up and stuff. I'm keeping it short today, guys, so I'm going to kind of now just show the resources here. So the resource here is, I kind of got really, I enjoyed going through this on Nepal here. I'm probably saying it wrong, but the Bose-Einstein, Fermi-Dirac, and Maxwell-Boltzmann distribution on YouTube. And I kind of went through, there's a lot more on there to this video, and they actually show the Fermi distribution as well. But what I wanted to do more with, but for lack of time today, is I found this really nice video, but it's too mathematical for what we're really trying to accomplish, for the high school class. But I like this, and this is something that has a conceptual tone to it, but it also steeps it a little bit in the mathematics as well. And it's nice. And let me just move down here for a minute. But this is called the Fermi-Dirac and Bose-Einstein Statistics, Basic Introduction by Dr. Physics A. And what he's doing is he's really drawing out these thermographs, which is really pretty cool and stuff. So I thought it was pretty neat. But anyways, so I'm really going to end on that note today, and it's it's been pretty good, and I really enjoyed looking at the material in the statistics course, and I'm looking forward to looking back on this material, and especially other videos on the Bose, Einstein, and Fermi-Dirac, and to get more of a view so that I can explain it better to students and stuff in the future. So again, thanks so much now, and that's all, guys. Oh, I think I clicked on the wrong video. So let me just end it here.